Cool. OK, thanks a lot, Alexi. Yeah, thanks a lot. So I'm going to talk today about making it easier to do parallel programming. This is something we've been doing in the Spark project for a while since we started the project, and also something that, that I believe we can continue to do even better, not just for distributed clusters, but for emerging parallel hardware and many other settings as well. And the key idea I'm going to focus on there is composition, which is something that we've learned and we've been iterating on since we started the project. So I'll talk about what's happening in Spark, also about the research that I'm doing at Stanford on new systems that do this. So if you step back and think, how are people productive writing software? What is the trick to make you productive writing software? There's basically only one trick, and that one is composition. That's really essentially the only way we have any chance to tame the complexity of writing software, is that we break the problem into little pieces and we compose those pieces to solve the specific task that we have. And that's essentially the only thing that we've had for whatever 50, 60 years that we've been doing software development. And it's kind of well known, but maybe people don't think about it all the time. This is one example. Like, why do people really like languages like Python? Well, it's not just the language, but just you can kind of import anything, and anything kind of works together. A functional programming person may say because they don't look at the types, they just try to make it work. But it is actually pretty useful. Or another example is programming via Stack Overflow. So actually in Visual Studio, there's a plugin that lets you, as you type in what you want to do, it just finds the relevant Stack Overflow snippets, and you can just cut and paste them to put them in there. And this is one of the best, most productive IDEs that we've developed. So that's composition. Everyone likes it. Everyone uses it every day. And it does make you more productive. But unfortunately, when you go to parallel computing in particular, and I'll also talk about other areas where this is happening, at least the early APIs that people came up with didn't really try to support composition as a first-class concept. And this created a lot of pain and, of course, a lot of data engineering tasks that you have to do just to build up your applications. So in particular, if you remember kind of the days of MapReduce and all the sort of dozens of parallel processing engines that people came up with, you had two issues. First of all, there were just separate specialized systems for each task. So you'd have to use one engine to do SQL queries, another one to do machine learning, another one to do just basic data transformation. And second, between these engines, a real application will need to use several of them. And between them, you had pretty slow data sharing. They all said, oh, I just write your result to a file and pass it into the next one. So if you look at Apache Spark and I think the single most interesting thing that it did, and the reason that it grew into a large open source project with a large ecosystem of libraries, is because it supported composition. So Spark provided a unified engine and API, and there were kind of two pieces. There was, first of all, the engine that could actually run all the types of computation that you're doing. But if you look at that, it's not that different from MapReduce. It's basically MapReduce plus in-memory data sharing. So it's not like rocket science to do that. And then there were composable APIs. So these functional programming APIs where you can hook together these functions, and crucially, you also get efficient execution underneath. So in particular, the API in the original Spark was this thing called RDDs, which is just this distributed collections of objects with functional operators. And you could do things like map and filter and so on. But the crucial thing underneath that actually made it possible to write stuff as lots of libraries is efficient composition. So when you do these operations, like when I do the map and filter here, Spark actually pipelines the execution so that each machine is reading one element, doing the map, doing the filter right away. It's not saving stuff in between as a file. And this happens even if these lines, instead of being right next to each other in the program, are coming from two totally different libraries that I imported that were written by different people who've never met. So for example, this thing might be the map might be like the Spark input source from some kind of storage system, and then the filter is my own code. And then within these, we also had a model for sharing data, which was just Java objects. Just give me a Java object and give me a pointer to it, and I'll work with it. So how well did this work? So I think in general, users really like this kind of unification, makes it much easier and simpler to build applications. But the way we did it, like the actual composition interface, was somewhat limited. So this original API caused some challenges, and these are the ones we're addressing. So basically in this talk, I want to, first of all, convince you that thinking about basically these software frameworks in terms of composition, especially efficient composition, is a good way to do it. And then I want to show you some of the new ideas in this space that go beyond the RDD API and even beyond the other APIs in Spark today. So first of all, like, do people actually use composition? Yes, people built a whole bunch of libraries, and most applications use multiple of these libraries. These are just the ones that are included in Spark, but then there are kind of many other open source packages out there. And then as you compose them, you get these nice benefits in terms of efficiency. So in terms of if you compare using these libraries in Spark versus just running separate frameworks, you don't have to write the stuff to a file in between. You can just run a pipeline sequence of functions in memory, and so you get high performance this way, or like higher than you would certainly in other ways. But there were also some challenges. So the main challenge is that the kind of function API I talked about so far, it looks high level, but it hides a lot of the semantics of the computation from the engine. And so the engine can't always do optimizations across your code that might make sense to do. So there's two reasons that it's a little bit difficult to do that. The first is that the functions are just arbitrary blocks of Java code. So I mean, yeah, technically we could imagine analyzing the code and figuring out stuff about them, but that's both very difficult and very brittle. You don't want your application, regressing 100x in performance because you changed a couple of lines of code somewhere. And also the data is stored in these Java objects, and that's kind of the model we have. That's part of the interface. So we can't do too much to make that more efficient. And the result is that users can mix the API in suboptimal ways. So for example, this is one really common thing that we've seen, which is users trying to do word count, but using the group by key operation. So this seems like maybe a nice way to do word count. You map each of these things into key value pairs, and then you call group by key, and then for each group you compute its sum. That seems pretty reasonable and looks very concise and nice. But the problem is the group by key operator. If you look at that operator, its signature is defined as returning a sequence of objects, here a sequence of ints. And the Scala sequence class is a collection that's basically materialized in memory. And so just because of the signature of this operator, we have to actually construct a collection in memory and return that. And that's really inefficient because for this particular task of word count, it's actually much, if we knew we were just going to do a sum, it would be better to do the aggregation on each node first maybe and then group them together, or like to not materialize this in memory but start adding them up as we read them. So that's something that we lose out on, and the engine can't do much about it because we set our interface as, hey, tell us a Java class you'll return and give us a Java function, and we'll run that for you. Now, this example might look kind of silly, like, okay, who's going to write code like this? And I do agree that, yeah, maybe an individual developer won't write this, or will at least debug it and figure out how to fix it. But remember what I said at the beginning, which is composition. So imagine that these things came from two different libraries. There's one library that maybe does the first two lines. It gives you, the groups of words, and someone spent time writing that, and you want to use it. And then there's a second library you want to call to do the sum. It would be awesome to write your program as just, I'm calling these two libraries, but now you don't have this optimization. So this is why this kind of optimization is important. So what have we been doing about that? We've actually been doing a bunch of stuff in Spark over the past, I'd say, 3 or 4 years to attack this problem through these higher level APIs called structured APIs. So I'll talk a little bit about those, and then I'll talk about going even beyond this to support more interesting types of composition in different domains through this research project at Stanford called Weld. So what are the structured APIs? Well, they're a new set of APIs for Spark that operate on what we're calling structured data. And what we mean by structured data is that it has a limited table-like data model where you've got rows with fields and so on. It's very similar to the data model in a database, or to the Hive data model, which has nested objects, or to something like Avo as well. So the point of this is the data model, instead of being Java objects like class whatever my.company.person, they're actually these objects with fields that the engine understands and data types that the engine understands. And then we have several different APIs that all map down to the same kind of execution engine. There's Spark SQL, which you can use to write SQL directly, but there's also DataFrames and Datasets, which are more for programmers, and they look more like the RDD API. And then these things support much richer optimizations across your application, similar to the ones you do in a relational database, but they try to retain the high level of programmability that you had with Spark. So how do these things execute? Well, whichever of the APIs you're using, we build up what's called a logical plan, which is just a concept in query optimization. It's a tree of operators. And then we optimize it. We look at what data is available to build a physical plan. And then we actually generate code that uses RDDs underneath to actually execute this. And then the final piece of the structured APIs is the data source API, which allows us to plug in data sources and also actually to push part of the query into a data source as well, which is a cool feature we can do here because we actually understand what the user's computation is trying to do. So I'll just give you a small example of DataFrames. Imagine people working with Spark have maybe seen it already. So DataFrames are these distributed collections that hold the rows with a known schema in the structured data model. And they offer relational operations on them, so the kind of operations you do in a database through a DSL. So that's a part that's different from RDDs. So you can create a data frame using SQL if you want. You can create it in other ways too. So in here, we're just connecting to a table, like say a Hive table that we have. And then you can do operations on it like filtering. I'm showing the syntax in Python because it looks a lot like the Python data frame library called pandas. And the thing, if you look in here, this stuff in the middle, user state equals California, this is actually this DSL we have, this domain-specific language that's building up an expression. And this is just an expression that means take the column called state and compare it to California and return like a true or false if it's equal. So this is just the abstract syntax tree for the expression. We don't actually evaluate it. We just have a way of building it up. If you compare this with RDDs, in RDDs we had to give you a Java function or a Python function that you execute that gives you the true or false. So we didn't understand what the function does. All we could do with it is run it and see what it gives. Whereas here we actually see the inner code in this kind of mini domain-specific language that we understand. And then you can do other things like count these ones after filtering them. You can also do grouping and aggregation. One note here is that if you look at this group by an aggregation, basically they actually reference the field names used in there. So the engine actually knows which piece of each record you're looking at, as opposed to just having to bring all the records together and run a function to figure out what you're pulling out from them. And then if you can't do things using the DSL, you can always fall back and write your own functions over them. It's just, it won't be as efficient, or like this will be a boundary where we can't do as much optimization. So that's what it looks like. Now, what do these APIs enable? So because we can understand the data model and because we can understand the expressions, we can do three pretty nice things underneath them. So first of all, we can have a compact binary representation of the data. We actually store data in a columnar format when you're caching it long term. We store it in a row format for processing, but it's never like a giant graph of Java objects with pointers between them. So it's actually just more efficient to store. We can do optimization across operators. So for example, we can push a filter before a join because it's only filtering one thing and so on. And we can do runtime code generation. So we can actually generate specialized code for the data types that you're using in your particular program, no matter how you put together that program. And of course, as you use this, it has a lot of the other nice properties that RDDs had. You can embed it in like a full programming language. You can use classes and functions and if statements and stuff like that to build up your computation. So it's nicer than just writing SQL, for example, as well. So how does it perform? So because the structured engine can specialize for your specific schema and your specific computation, it often can actually perform better than RDDs. Of course, it depends exactly what you're doing. But if you see in here, the DataFrame API, at least in this kind of aggregation benchmark, it did a little bit better than RDDs in both Scala and Python. And it didn't matter what programming language you're using, because underneath we're compiling everything to the same kind of optimized code. So that's another nice thing. Usually in Spark before this, you had to worry about like, oh, if I use Python, things will be a little slower because I'm just calling into Python all the time. So this is just briefly what this gives you. And we also offer kind of other APIs on top of this. So I talked about SQL. Another API we offer is called Dataset, which adds static typing. So kind of like, so basically you have your data frames as before, but you say, okay, the schema of the data in this will correspond to this Java or Scala type. So as an example, let's say we've got two classes in our program. You can use case classes in Scala to represent your data. Let's say we have user and message. We can read a data frame using just the standard Spark APIs for that. And then we can tell the system, hey, we want to view this as a bunch of message objects. And actually at analysis, like when you're running this code, it will look and see whether the schema matches that. So it will actually tell you that, hey, these things don't look like message. They don't have the fields user and text. And then we can do operations on them where we view these things as Java objects. So, things like filtering and mapping, where we just view these. And actually, Spark preserves the data types through this. So, for example, when we map m to m.user, we go from a dataset message to a dataset of user. And if we want, we can also go back and use the full DSL available on DataFrames and do things like group by and just specify this string in here that we're going to deal with. So this is a nice way to combine kind of the benefits of the statically typed Java object type API in RDDs and of this one. In particular, if you're writing a big piece of code, you can document all your functions as returning data set of a specific type. So you have, you understand the typing as you work with other people on your team. Everyone agrees on what's going on in the data. And you can still use these more optimized kind of operations underneath. OK. So that's just a brief overview of why these work. Hopefully, it gives you a sense of like what they enable that's more powerful. Since we started this work, I think this started around 2014, we've actually built a whole bunch of other APIs on top of these structured data frames and datasets. So for example, data sources for Spark, machine learning pipelines, and graph processing and structured streaming. So I'll just show you a couple of examples of what you can do and why it's powerful. So data sources, this is the standard way to connect Spark to a storage system now. Basically, the part that's interesting about this API is that it allows query federation into the sources. So as you're writing your computation, for example, when we had that filter expression before, Spark can figure out which filters apply to this specific data source, and it tells the data source, here are some filters for you. And if your data source understands these, it can actually push them into the storage system and avoid reading all the data into Spark. This is something that would have been very hard to do with the original system. So just as a simple example, let's say we've got a JSON file. You can view it as a bunch of records using Spark and have fields like user ID and so on. Let's say we also have a MySQL database, and we want to select some stuff from it through JDBC. And let's say that we're actually trying to combine these two data sources. So we're trying to combine appropriately enough for Twitter. It's about tweets. So we're trying to get the tweet text and the user age. But the user age is in a database, and the tweet text is in some kind of JSON file, because that's what Twitter gives us. And we want this filter on user language equals English. So actually, Spark can look at this query and decide, OK, from the database, we only need ID and age, and we want to only filter on language equals English and put that in. And again, if you go back to what I was talking about with combining libraries, don't think of it as like one developer knew they have to do all this in advance, but think of it as someone wrote a library to, like, say, load the users for you. Someone else wrote a library to analyze tweets, and you're trying to hook these together and still get good performance without having to dig into each of them and plan out your whole execution. So that's what it does. And then the second example I want to talk about where this is powerful is structured streaming, which is the high-level streaming API built on DataFrames and datasets that came out basically last summer, 2016. So this is kind of a higher-level API that tries to keep all these properties, the query optimization and so on. It supports things like event time processing, windowing, stateful operations. And one of the goals is to support these end-to-end, what we're calling continuous applications, where you're not just receiving stuff in a stream, doing a map function and writing it somewhere, but you're trying to write a complete application that might involve interactive queries, batch jobs, and so on. So it's designed to make it really easy to interact with the other parts of Spark to do that. Now, the really cool thing about this is actually the API. So we added this whole streaming engine, but we didn't really have to add a new API. Instead, the way we do it is that we incrementalize an existing query you have using the structured APIs. So as a small example, imagine we have this batch job here. This thing is just a batch job. It's trying to read some JSON data from HDFS and then group it together by the user ID and also the hour field. So this is like the event time when something happened, and figure out the average latency. And let's say we're trying to write that to a file in S3. So that's kind of nice. We can understand what the job does and save it. If we want to make this into a streaming job that updates the result incrementally as new data arrives, we just have to change the input and output methods. So from read to read stream, and same thing for write. So all we have to do is say, OK, well, we're now going to read a stream. Just keep looking for new files in this location. And then we do the same grouping. And then we're going to write to Parquet, and we're going to actually update the counts in this Parquet table over time. So inside, you run the same operations as before. And because Spark understands the expressions that you're using in there, it knows how to actually incrementalize the computation for all of them. So what it will do is it will take this batch query plan that had a bunch of operators and just transform it into an incremental plan that includes keeping track of state and updating this thing, I guess MySQL or S3, updating it transactionally so that you see the right values appear. So it's a pretty powerful API to do streaming. It's really easy to use. If there's anyone in your organization who knows SQL or DataFrames, they can use it. It's really easy to test because you just switch it to batch mode, and you can just run your code and get a result. It's only really possible because we can look inside these operations and understand them after you've put them together in your program. Just as examples of this is a pretty new API, but we've actually seen very fast kind of growth in usage. So at Databricks, which is the startup company I co-founded, we run a cloud service, so we can actually measure and see how many people are using the API. And there are already hundreds of customer applications running in production. So these are things running 24/7, the largest of which process tens of trillions of records per month. Some example applications that people have given talks about are monitoring live video streaming delivery on most of Viacom's web properties, anomaly detection at iPass, which is actually the world's largest operator of Wi-Fi hotspots, and also real-time analytics for League of Legends from Riot Games. And the cool thing across all these use cases, actually the thing I'm most surprised by is how few issues we see in terms of support tickets and so on, because people, if they already know how to use SQL or DataFrames, they can write something, kick it off, and it just runs, and they don't need to learn a new API and get confused by it as it's going along. And we've also spent quite a bit of time optimizing the performance here. So because this engine builds on Spark SQL and on Tungsten, where we spent tons of time, making it competitive with kind of an analytical data warehouse, it's actually pretty fast for streaming as well. So for example, we ran this Yahoo streaming benchmark that a bunch of systems optimized for, and just out of the box, we got about 4 times higher throughput than the next fastest result that had been published for this, which was from Apache Flink. And we didn't have to do anything special to optimize the code here. It's just the code for doing aggregation and selection and so on in Spark SQL was already optimized for that. So the really cool thing about this for streaming is, of course, if you're streaming, you're running something 24/7. So if you can run the same thing with 4 times fewer resources, that can save you lots of money, so that's pretty good. And there's actually also an operational benefit. If you can run the same thing on 4 times fewer nodes, it's 4 times fewer things that fail, 4 times fewer things to upgrade, and so on. So we think actually, basically, per node performance is probably even more important in streaming than it was in batch processing, because batch processing, you're often bound by just reading stuff from some kind of slow storage. So that's one other thing that if you want to look at what's happening with the structured APIs, this is where there's a lot of activity today. OK, so in the final bit of the talk, I want to go a little bit beyond this and say how I'm taking this idea a little bit further in research at Stanford. So this is not necessarily stuff that's in Spark or that's kind of production ready, but it is interesting to try to take this further. And partly from seeing what people were able to do with these APIs in Spark, I've been very curious to see how far we can push them. So at Stanford, we've started this project called Weld, which is trying to design the same kind of composition-based, efficient programming interface, but for modern parallel hardware. We're really targeting things like multicores, GPUs, and potentially programmable hardware as well. So the motivation is that with continued changes in hardware, actually even your local machine is a distributed system, and going to memory is very slow. So memory is sort of the new HDFS. If you're just putting stuff in there, it can be much slower than your computation. And this means that the traditional interfaces we've used for composing libraries just on a single machine are increasingly inefficient. And actually, we see this with Spark workloads as well. Often, we get things that are CPU and memory bound on each node. It's not the network that's a bottleneck. So what do I mean by traditional interfaces? Well, so the traditional way you compose software on a single machine is basically through function calls. This is something that we've had pretty much since people started writing, kind of structured programming languages. And the contract of these is pretty simple. It's basically, OK, you put some values in registers, maybe, and you jump to a piece of code. And usually, to pass in a large amount of data, you have to put it in memory and pass a pointer to it into the function. So basically, write your stuff to a memory buffer, call one of these functions, and let it run. But if you look at a lot of computations today, they don't do a lot of work per byte of memory. Or more accurately, what I should say is memory has gotten much slower relative to CPUs than it used to be when these interfaces were designed. So as a simple example, let's say I'm just doing some simple data transformation. I'm just going to show this in Python. But actually, even in Python, when you call these functions, each of them is actually written in C. So it's not, the problem is really not the Python. So let's say I've got one function that parses CSV files. So I've got my data in memory, and maybe I parse it to get a table. And then I've got another function to drop the NA values, and I've got another function to compute the mean. This is going through essentially the whole data, reading and writing about 5 times. Whereas in fact, much like the pipelining in Spark, if I just knew I would have to do all this in advance, I could just go scan through at once and compute the mean in a running fashion and not have to do all this stuff. And again, when people first designed these programming languages, it took 1 or 2 cycles to access memory. So basically, if you wrote a function and it had to go to memory, it wasn't a big deal because you're going to do some computation on each byte anyway. So it's OK if you take a cycle to get it. But now it can take basically the equivalent of hundreds of cycles, and so the memory kind of transfer costs can dominate. And if we look at workloads in today's frameworks, we see that often for data-intensive workloads, this creates very large overheads. Even in systems where each operator and each function is optimized by hand, like NumPy, where some scientific programmers sat down and tried to make each operator really efficient. So how can we fix this? So basically, in Weld, we're trying to build the equivalent of a runtime for data parallel computation, similar in some ways to JVM or to the Spark SQL runtime I talked about. So we're going to have this runtime where people submit snippets of computation, and then we actually optimize across all of it and produce efficient code for the whole program, not just for these individual ones. And there's a few important pieces to this. So first, there's the API that libraries use to actually submit code. And then there's this common IR. This is a common intermediate representation for data parallel code. This is kind of the equivalent of the logical plans I showed before, but we're actually trying to capture more types of computation here. And then we have an optimizer, and we have these hardware backends. So let me just start by talking about the API. This is actually pretty simple conceptually. It just uses lazy evaluation, similar to Spark, to collect bits of work to be done. So as you're running different functions in your application, instead of executing eagerly, they'll each just push a bit of work into the runtime. They'll say, hey, I want to run this computation, and here's kind of a handle to the result. And then at the end, you can actually force it to execute, and then it will look across all of these and do something. It's actually interesting to compare this with APIs like OpenCL and CUDA today. So people use these to get high performance. People will write key parts of their code in OpenCL, but all of them execute eagerly. So there's no way, if you have several different libraries using OpenCL in your application, the system doesn't do any kind of optimization across them. So you can think of this a little bit like a lazy evaluated version of that. OK. And then the second component is the IR. So what is kind of the language in which we submit code. And this is where we try to go beyond the kind of things you get in Spark or in a database with a more general language that can capture more things. So we have this really small but powerful IR inspired by something called monad comprehensions. And it just has 2 constructs. It's got parallel loops, which let you iterate over a data set. And it's got something called builders, which let you produce results. And builders are kind of abstract data types. So an example of builders is you can have a builder that adds objects to a list. Or you can have a builder that computes a sum. But we can implement these differently based on the target hardware. And we abstract that away from the programmer. How exactly will compute a sum, say, on a GPU? So just as a few examples of implementing stuff using builders, I'll show how to implement some functional operators. So let's say we want to implement map. We've got a bunch of data and a function f. we can basically we can create this thing called vec builder, which is going to append stuff to a list. And then for each item in the data, we can merge f of that item into the final list. And this is this loop happens in parallel, and actually the builders are all associative, so it preserves the order of these things. And then the last operation you can have on builders is called result, which takes it, finalizes it, and gives you back a value. So that's what it looks like. If we want to do reduce instead, the code actually looks super similar. The main difference is our builder, instead of being this thing that makes a list, it's something that merges values with an associative function. And now for each item, we merge it into there, and again, we call result, and we'll get that back. Now, the cool thing about this representation is it's also easy to represent fused operations and just basically ways you're going to optimize this execution. So for example, let's say we have a program that's computing two things over the same list. You want to compute a map to build the squares, and you also want to compute a reduce over the same data item. If you were just going to write this by hand, you would probably just write a single loop that does both of them. And in Weld, if we see the bits of code that came from what I showed earlier, we can automatically fuse them to do something like that. So it's easy to represent that. And beyond this, we can actually do a bunch of other optimizations like loop tiling and vectorization that also greatly improve memory efficiency and require this kind of end-to-end view. So how does this actually perform? We tried really kind of rough prototypes integrating this into different systems. And we see that just by adding Weld underneath the existing API, so without changing the user-facing API, we can get somewhere like a 5 to 10x speed up over the naive way of running these things. For TensorFlow, I don't show it here, but the hand-optimized code is also similar to the TensorFlow XLA compiler. So, our pretty small and general language can also match that. And for NumPy and Spark, we get about a 5x speed up. And then if you have a workload that combines many systems, there's no way that today you'll get great performance, even if they each implement their own compiler. But with Weld, you can actually do that. So this is showing Weld without cross-library optimization gives you about a factor of 9 speed up. With cross-library, it's a factor of 30. And then Weld is also, the language is explicitly parallel, and you can run anything on multicore. So if you run it on multicore, you can get a further speed up too. So overall, we think there's a lot of space to greatly improve the performance of current tools and to keep programmers productive. So we're working to build this out and also build a bunch of libraries on top of it. If you want to find out about it, it is implemented in Rust, as Alexi said. I can talk offline about what's good about that, but it's actually kind of fun to work with. And it uses LLVM for code generation, and we've open sourced Weld as well as a port of pandas to run on top of it. So you can check it out online. And then the final thing I want to just briefly mention is we're also using this approach in other research projects. So for example, similar to the data source idea I showed for Spark, we have a system called Sparser, which generates parsers and I/O paths for your specific query. This actually goes all the way down to generating SIMD instructions on the CPU and trying to vectorize it to make it very fast. And we see pretty large speedups there as well. So we think this idea of assuming that developers will just want to compose stuff and then trying to design interfaces that lets us optimize under those has a lot of legs. And we're trying to do a bunch of stuff in my group to take it further. OK, so that's pretty much what I wanted to talk about. Basically, in short, if we want to be as efficient working with modern hardware as you were working with a single CPU, we have to change the way we compose software. And it's the only trick we have to make it, not rocket science to do that. And Apache Spark and Weld are just 2 examples of projects that are going towards this goal. Thanks. Do we have questions, or do we? I don't know how this works here. Yeah. Do we have time for questions, Alexi? OK. Yeah, sure, go ahead.
So thanks, that's very inspiring. So you talk about optimizing like corporations or corporations. You talk about optimizing on the weak side. Yeah. Another type of optimization that people often do is like large-scale memorization or caching of the intermediate results. Yeah. Are you thinking about that, or do you have any pointers?
Yeah, that's a great question. Yeah, actually, we try to do a little bit of that in Weld, but we're not doing it. In a super principled way. But we do see workloads where you compute the same thing over and over, and we could analyze it and figure out, okay, let's save this thing once. Yeah, it does. It definitely can help, and it happens by itself. Yeah. Yeah, at the back there.
Back in 2015 Spark Summit, there was a project presented called Heterogeneous Spark, which is a Spark running on GPU. If we have this Weld Runtime, will we be able to, in the future, extend over to, let's say, OpenCL and other libraries like heterogeneous computing frameworks, so that Spark can eventually run not only in CPU but also leverage other part of the running process?
Yeah, that's definitely one of the goals. So it has kind of a couple of goals. One is to decide if we can even get good performance from composing libraries this way. And we think we've shown you can get a bunch. But then I'm also really excited about the way we abstract over different hardware. In particular, the concept of builders. Basically, when we looked at how do people have to change their code to go like from a GPU to a multi-core or to like a Xeon Phi or something, the hard part is usually the synchronization, and that's all encapsulated in the builders here. So like we think that actually it's not too hard to make this code portable across these, and we're working on that as well. And the kind of the cool thing with that is we think it's like super important for the industry to have a standard IR to do this stuff. Like you can't really innovate in hardware today without convincing people to switch software to use it. And this thing would allow you to innovate in hardware much faster. Yeah.
I think that's all we have time for. Thanks a lot.
OK, thanks.
Do you have questions?